Okay, so my name is Richard Burke. This is Harry Ray, and this is Pat O'Connell. Um, Harry Ray is from Energy Awareness, Pat O'Connell is from Burkine, and I'm working with Burkine myself. Now, Harry Ray has come along today to have a quick chat with us about hot water gravity circuits. So, hopefully, we'll get a bit of information today from various systems. So, I'll give it off to Harry here now.
Right, lads. Just starting off, I've noticed over a period of time that people have a kind of a wrong impression of how gravity systems might or might not work. Some people have the impression that when a stove is lighting or a gravity circuit is moving, that the water wants to move around in a circle. That's completely wrong. Hot water, or water that's lighter than other water because it's hotter, wants to rise. So you know that if you heat the water in a cylinder, the hot water will lodge at the top of the cylinder. The same would apply with a solid fuel system. The difference is that in a solid fuel system, when the water is rising up through the pipe or very long cylinder, as it travels towards the top, for it to travel, it leaves a space behind, and that needs to be filled. So basically the water that was up in the top before moves back down the return pipe to fill that space, and the hotter the water gets, the faster it moves, and the greater the kind of vacuum it leaves behind as it's rising upwards. So the point is that when it's rising up and it gets to the top or up high where it needs to go, if you have a heat leak that strips away the heat, now the water that was up there is heavier and it starts to fall. If that's in the path back to the boiler, you have two reasons why the water will circulate in a thermosiphon. One is the lighter, hotter water is going to rise up, and the second is very simply because the heavier water, which has been stripped of its heat, wants to fall down. The point is that you can't interfere with that circuit with any valves or any obstructions, and more importantly, there should always be a way for air to escape so that water will have a free path around the system. So we'll move on and we'll look at a few systems. If you look at this diagram, you see we have a representation of what could be classed as a standard heating system. You have a container that might be heated by another source of water, let's say a barrel of water, and when the water is in the barrel is hot, if you pump from the barrel and you're pumping towards an expansion, where is there pressure? There's pressure between the pump and the expansion, and from the expansion on there is a pressure, but it's a less pressure, so the pump is just as likely to push water up and through the expansion and back into the tank as it is to move it around. As the water moves around the system through the heating devices, it's actually only filling back into the barrel to create or to fill the gap of the water that's being pulled back out. So that's the wrong way to do it, and in a lot of situations where a pump is in front or expansion is in front of the pump, the system will be continually full of air or not circulate properly. In this situation, we have the pump pumping behind or from the expansion towards the neutral point. The neutral point in the system, remember, would be where your expansion tank is. So if you can imagine, the top of the barrel there is represents the water at the top of the expansion tank. So if you're pushing towards the neutral point and your expansion is behind, there's as much chance of you pulling air in through the expansion as there is of pulling water around the system. So again, you've got a problem because the pump can't act properly on the system. What you really need to do is you need to pump from the neutral point with the cold feed coming in between the expansion and the pump, so that you're pulling water from that whole volume of stored water and pushing the water around the system through the devices, the radiators and convectors or underflow, whatever, and back to the neutral point. In that instance, any air in the system can be lost at the top of the water in the expansion tank or go out through the vent, and the cold feed will fill in any water that's needed as the pressures move within the system. So that's the perfect system for an open vented system. If we look at a standard central heating appliance, standard solid fuel stove, could be a cooker or a back boiler. If you look, let's think about the barrel for a second. The water on the top of the tank is the barrel. The expansion in that situation is on a neutral point because there's no pump by using 4 pipes off the barrel. So any hot water rising meets the coil, the water in the cylinder cools the coil, the water gets heavier, falls down and back to the stove. So you have a perfect reason for the hot water, having been heated by the fuel, to rise, be cooled by the water, falls back down. In the meantime you have an open expansion and you have a cold feed. So that's the standard, very natural way for a thermosiphon to work. On the other side, if you're pumping from the other side of the stove, you have full pressure leaving on the pump, heading out to your radiators or whatever system you have, and coming back again to your neutral point. Again, a very good system, 4-pipe system. The same thing applies if you have a 2-pipe system. Some people think it's even better because you have a definite amount of water that's doing a very definite job. Where the water leaves the stove and heads out, it meets a T. It can rise up by natural occurrence, by thermosiphon, is cooled by the water in the cylinder, falls back down. You might notice the loop on the cold feed coming down, where the cold feed comes down into the system. That's to prevent any drifting hot water rising back up into the expansion tank, because if that water ever gets warm, it will evaporate faster, and if it evaporates faster, it has to be filled again with mains water, and therefore you're introducing fresh oxygen into the water, which will rust the boiler and pumps and radiators. But on the injector side of the system, where the pump is pulling water from the system, it shows here where there's a downstairs circuit and an upstairs circuit. The pump is pushing it through an injector T, which is a narrower piece of pipe within the T. As it pushes through, it causes a vacuum above the centre of the T, which pulls the water down from the cylinder, and it fires the pumped water through the boiler, but also induces a flow on the gravity circuit through the cylinder. So an injected system, very good, normal systems, highly recommended by most boiler manufacturers. Again, we have practically the same system, except now we've gone up to a high level, travelled across and back down. But if you think about it, the cylinder is still higher than the stove. So there's no reason why the heat won't try to find its own level. It travels up from the stove, and as it does, it levels out until it meets the cylinder. The cylinder water cools the water in the coil. The cooler water wants to fall down. In falling down, it pulls more hot down through the flow pipe, and therefore the more coming down, the more the cold is forced to head until it goes up and across back down to be heated. The little 1/2-inch bypass valve you see here is a very good idea, because if you bring pipes up and across an attic, the danger is that you would lodge air in the return pipe. The vent pipe has an open vent obviously above the tank, but the cold feed with a little 1/2-inch bypass valve between two barely open will allow any air that's trapped in the return pipe to rise up from the return to the flow and then out through the open vent. So in effect, the thing to remember about that system is that the cylinder or heat leak is higher than the stove. If the cylinder was down at the same level as the stove, it would circulate very badly, or maybe not at all. So the cylinder must be higher than the stove, and obviously the higher the better. Again, you see there's an injector in front of the pump doing the same situation. You also see with solid fuel it's very important to have a safety valve as close as possible to the appliance. I'm inclined to think a safety valve should be on the neutral point of the system, on the neutral circuit, and not on the pumped circuit, as it's just less likely to pick up any debris or whatever like that that might cause an obstruction. This is probably the most typical system, and there's a problem with it really. When you take a flow from a stove or a back boiler and you rise up and go down to heat the coil, it heats perfectly well, falls back down across the floor and up into the stove through an injector T again. But the problem is when the stove goes cold, the cylinder water can reverse back up, go up through the same pipe and lose heat in the attic. It's critical that when you put pipe in an attic at any given time, that you would make sure it's insulated, and in my opinion, insulate the insulation. So in other words, double, maybe even put fiberglass and polythene around the insulated pipe, but you want to make that pipe like a flask in the attic. But still that system has the dilemma of the hot water reversing back out of the cylinder.
And just to add to it as well, lads, this is very close to the system that I have at home. The only added extra is that I have solar, and I had solar in this as well. And as Harry said, it did reverse. It did start reversing out on me because the solar was heating the cylinder, and it started reversing back out and back up into the cylinder and losing heat. It was losing an average of about 40 degrees a day because it wasn't insulated properly.
Harry, what's the significance of the injector tee?
Well, the injector tee in that situation just causes that you have a perfectly open circuit because there's no valves, there's no obstructions whatsoever on the circuit. But at the same time, when the pump comes on, it creates a vacuum above the entry of the return into the circuit, and it pulls the water up out of the floor in that instance, and causes the water to circulate much, much better. The good thing about an injector tee is that you can kind of control the amount of water that's passing through the cylinder, but the vast amount of water, when your stove is up to temperature, goes through the radiators, which is exactly what you want to try to do.
Yeah. Okay.
Again, here's just another similar type situation. Cold feed is brought down as close as possible to the boiler with a heat lock loop, so the heat won't drift back up into the tank, and otherwise an up and over system. But this is a 4-pipe system where you have your pump pumping from, say, the right hand side of the stove, and your no pump on the other circuit, and it just works away on gravity on one side with the pump on the other side. It's an excellent system, really.
And how open should the valve be at the top there to allow the air to go through?
Just enough to let the air pass, but I would not have it so closed that it might ever obstruct, because obviously it's a critical pipe not to have air in.
Yes.
I would have it open, and maybe let's say there was 10 turns, I might have it open 1.5 or 2 turns.
So just cracked open.
Beyond cracked open. Yeah. Here's again a situation. I know there are other devices on this, and we're not particularly talking about them today. So all I'm really concentrating on is the flow and return off the stove, how they rise up through an energy link in that situation, but forgetting that, comes to a high point first and then falls across the attic. To my mind, that's the very best system, because you have your high point catching any air, and also when it comes back down and the cold water the water has lost its heat and rises back up, it rises again to the high point where the half-inch vent is, and that vents all the air out and back down again to the stove. So you've got your neutral point, or the top of the barrel, is created by the top of the tank, of the expansion tank in the attic.
So for gravity feeds, basically, what you're saying is that the cylinder always has to be higher than the bottom of the cylinder.
If the cylinder isn't higher, it just can't work. Hot water wants to rise. It rises in cylinders when you turn on the immersion. It rises in the matter. So if you have to allow for the natural occurrence of hot water is lighter, is less dense, it wants to rise.
Yeah.
Here again is a situation where you could have, say, a dual system. Again, we're not really focusing on the dual system aspect. But in this, if you follow the flow up, you see that it can pass through to your secondary system, secondary being your motorized valves or manifold or whatever. There's an open path for it to go down through the coil, and so that's a priority hot water situation where the stove has an open path to heat the water first. If a stat is located down on the return close to the stove, and it's set at, say, 55 degrees on the return, or sometimes 65 degrees on the flow, it will turn on the boiler pump or the stove pump. If that pump is turned on, for the first time now it pulls water through the secondary system, say the manifold, and now your radiators can get some heat. But that's hot water priority. You're making the hot water heat before you decide to have central heating.
Is this setting on the stat, Howie, is that critical?
I think it's extremely critical, and because I've always felt that you can't trust the numbers on a stat, what I typically do is turn on the system, light up the fire, turn the stat up to 90 while you're present, stay with the stat, and then when you just can't hold the pipe, a strange fact is you can just about hold 58, 59 degrees. You cannot hold 60 degrees. When it's just coming up towards that temperature, turn the stat backwards from 90. Obviously it's wired, so it makes a circuit when the temperature is rising, and when it's just less than what you can actually hold for a second, you bring the stat back where it clicks. If it happens to be 55 degrees, let it there, but I'd rather go by that method rather than going by a number on the stat, because the stat might be out of calibration.
And there seems to be an awful myth as well, Harry, about having them on the flow instead of the return and vice versa. Is there any beneficial to have flow or return for the stat?
It's a very good question. The reason that I'd be inclined to look at flow or return, if there's a chance that your system hasn't got a very good gravity circuit because it's at furthest that might be allowable or practical to use, I'd be inclined to put the stat on the flow, because then you know if the water's starting to get towards 65 in a solid fuel stove, you should be turning on the pump. Whereas if you have a good circuit and it's circulating very well in the gravity system, I'd put the stat on the return and set it at 55. Can I say there's a really important thing to talk about with solid fuel? If water ever reaches above 80 degrees on a return pipe or on the flow in the stove, the amount of pressure between the temperature rising water and the falling water is perhaps negated, because it's so minimal that in fact the thermosiphon might stop working. And that's why I don't particularly like devices that rely on flushing water, whatever. You need the water to move, and you should be moving it well before it ever gets close to 75 or 80 degrees.
There should be good circulation at that point before you hit
It's
that.
very important. But obviously I can't understand how anyone would...
What's the danger with 80 degrees? Why 80 degrees?
80 degrees is when the water coming back to the stove reaches 80. Between 80 and 100 there's very little difference in the density of the water, and the thermosiphon starts to slow down completely.
Okay.
Now this is just the same type system, except it's hot water, it's central heating priority. Forgetting the fact that it's a manifold, if it's motorised valves or whatever, the flow goes towards the distribution system first, and when that is satisfied, there's a bypass within the energy zone manifold, as with other manifolds, and when it goes to that, then it passes the cylinder flow and drops down. But if in the meantime you want to steal away the heat with your zones before it gets to hot water, you can control the temperature of your hot water by having a cylinder stat that won't allow the pumps to run on the zones until the water is satisfied. Obviously that stat is nothing to do with your primary stat, because that stat must always turn on the pump. You always have to have a primary stat.
So basically that cylinder stat is only controlling your pump, basically.
It would be used to make sure that the water has a chance to get would get warm, but at the same time you can steal the heat. You can heat the cylinder with the return water, which you should still keep above 55 degrees, but it means that you can control the temperature of the cylinder, which really is unheard of without that type system.
What does that stat then actually fire? What does
That
trigger?
the boiler stat brings on the boiler pump, whereas the other cylinder stat could prevent radiator zones from coming on. In a motorised valve system would be called a W plan. An S plan is where you'd have the two motorised valves. The Y plan is where you'd have a Y shape or a T shape valve, but a W plan is where you'd have the hot water satisfied before the zones come on.
Just to clarify that, what does the pipe stat and the return, what does that actually fire?
It turns on the pump, the boiler pump down at the end next to the stove.
Okay, that pump here,
The pump on
above the injector T there.
Yeah.
Yes. And what does the cylinder stat
Well,
do
the cylinder
then?
stat, if the other oil boiler was on, you see, as well, and you want to control your domestic water temperature, you need a stat on the cylinder anyway. But you can configure a stat, maybe not you might need an extra stat. It totally depends on the job, but you could have an additional stat that would say only, or turn on the zones only
when this is at a certain
when it's
temperature.
at a certain temperature.
I'm with you.
Or you might turn on extra zones when it's at a certain temperature, but you might have one zone or two zones come on first, but then you might keep all of the circuit off until the water has reached what you decide is your control temperature, and then you bring on the rest of the zones. It means, as you say, you can have full temperature control over hot water even though you have open primaries.
With you.
In that system, really, there's a couple of unique things, but if ever there's a problem with pitching where the expansion has a pushing water up over the top of the tank, you can put a half-inch feed from the expansion across onto your cold feed in some situations where the two pipes are joined close together as they attach to the neutral point, so that you don't have a movement of water through them, and that if the water ever builds up on the expansion, it'll fall down through that bypass pipe across and into the cold feed, and it will stop the system pitching.
And what's that there then on that Just here on that half-inch pipe coming
That's a
across.
non-return valve. Sometimes it's needed, sometimes not. It would face towards the cold feed so that it's not to allow water to circulate backwards.
Oh, I'm with you.
It's to only if water builds up in the expansion.
It is a flap type, isn't it?
It's a flap type valve
Oh, yeah.
and fitted on a very horizontal pipe. So
It
that
has
the
to, has
gate
to be
is,
flat, so does it?
it has to hold just barely opens on a horizontal pipe.
Oh, yeah.
There's no point having it on a vertical pipe because the gate would be too heavy
I'm with you.
and the gate would hang open anyway.
Mm.
Anyway, on that there's two solid fuel appliances. Solid fuel on the left has open primaries into the manifold, energy zone manifold, and the solid fuel on the right has a separate set of open appliances. But in that situation, if you see, the cylinder is very unusual. There's a flow pipe that hasn't got a valve coming back to a return through the coil that hasn't got a valve. But you see the third connection on the top feeding through a pump and into an injector tee. You can actually put faster water through the coil if you want and heat the cylinder quickly, and yet you're not interfering with the open circuit of the coil. But the main benefit is you've only got an indirect cylinder and yet you've got two appliances.
I was just going to say it there, Harry. There's only one coil on the cylinder, yet there's two appliances.
Well, what's very important is the
That's still
size
the-
of the coil is very important, because if you have a standard 3 kilowatt coil, there's no point putting that onto two cylinders. So it's very important that the coil is able to handle the setback temperature from the two stoves when they're in turn down mode. Turn down mode means when the stoves are lighting and the cooker is lighting, but that their dampers are closed completely. The coil should be able to take as much of that heat as is possible.
But that is your heat leak, so really basically.
The cylinder has to be able to take the two lots of heat leak from
I'm
each
sure.
stove.
Okay.
Again, now here's a situation where you could have, say, a stove maybe in the ground floor, cylinder upstairs, and again you just rise up and drop down on your flow through the coil and back up around again. But you remember the problem we mentioned a while ago? Well, first of all, you're venting the return on that valve, but also the heat is allowed in that situation to drift back up from the cylinder and heat the pipe in the attic. So it's not necessarily the best way to do it. We can talk about how to fix that secondly. On the other coil, just a matter of interest, that's where the second boiler could be through a motorised valve or through a manifold. We're showing it through an energy zone here, but on any other system. So the second coil is used for the secondary system, in that instance an oil boiler. Now, this is an interesting job, because if you follow, forget the energy link for a second, if you follow the flow pipe up from the stove, it passes directly up, no obstruction, it has an open expansion, it has the cold feed coming underneath, it's travelling across, it passes down below the coil of the cylinder, right down to the end of the cylinder, and then there's a separate feed upwards through the coil. So we've created a sub-gravity circuit. That sub-gravity circuit heats when the first circuit heats, and now the cylinder can draw heat. But when the cylinder is drawing heat, the water heats, and so the water falls back down through the return and back down across the floorboards, back down to the stove. But if the stove ever turns off, the heat is trapped up inside in the cylinder. You see, in that instance there's a half-inch vent pipe. That wouldn't be classed as an expansion. That's a vent that releases any air that might potentially get trapped in the coil. The actual expansion of the system is a critical part of solid fuel, and that's the 3/4 expansion or 1 inch over at the top
Bill, is it?
right hand side over next to the
No,
expansion.
on that note, lads, if there was my solar system in place, this is a potential fix, because if the solar was done below here, shall we say, and it was heating the tank and what have you, it can't get back out. It literally cannot get back out.
So you've created what's called a heat lock.
Yeah.
And so it stops the problem with heat drifting back around
On
the
that
attic.
particular drawing, now, Harry, is the distance between the cold feed and the open vent, is that critical at that point there?
Very important that it stay within 6 inches of each other, because it just stops any chance of water activity. If two T's are touching each other, heading away, the pressure differential as the water is passing is minimal. But in that particular situation, you see, there isn't actually a pump acting on the primary circuit, so it wouldn't be as critical as if it was if there was a pump passing through.
And the reason for the venting, is that because you're rising back up again here, or not for the vent, for the to release of the air, the half-inch pipe
half-inch
coming
vent,
up.
just
Is that because you're rising back up again?
It's just because there would be air lodged in the coil of the cylinder, and that half-inch vent just releases that air.
Very
Very good.
Again, this is just a similar type situation where you have an open primary circuit passing through an energy link, but that really isn't the point. The cold feed is what important there. Do you see how it's brought down? So it's the last connection on the way back down to the stove. So if water is expanding and pitching, the cold water can travel down through the cold feed and get at the stove to cool the appliance. Yeah. And then again you see the heat dropping down, or the loop dropping down. Obviously the lowest point of the loop as it drops down beyond the cylinder is still higher than the stove. So whether it goes up to the attic across and drops down, it doesn't make a difference because the stove is lower than the lowest point in the coil below. So that says you have a heat lock loop preventing backfeed and you still have open primaries. In that situation, same thing, is just a different configuration of the same idea, but in here you could have an energy link in, say, an attic situation, and your energy zone in an attic situation, or an upper room.
And which is sort of like this is the ground floor, next
be,
floor,
say,
and
bedrooms,
that's the attic then, like, yeah.
So obviously when all the pipe work is done in the attic, an energy zone comes pre-insulated, but even still it is so important that you do by far better than normal lagging, because if those pipes ever freeze, you've got a danger. So I do understand that there's a safety valve next to the solid fuel, but you cannot rely on a mechanical valve to keep people alive or safe. So you have to have an open, completely ice-free solid fuel circuit. So the gravity circuit there is critical that it's insulated extremely well for two reasons. The minor reason is that it's going to keep energy. The major reason is that it keeps people very, very safe in cold conditions. Again, up, over and back down, around. Now here's a very unusual situation. If you follow the flow, you see it travels up, goes across the attic, but it needs to get through the heat exchanger and the energy link, so you pass down below it, spins around, back up, through the energy link, down through the coil, and then cooled by the coil and falls back down. But now it's being drawn back by the cooler water falling down along the pipe towards the stove. So you have a vacuum pulling down on the stove return, and you have a pressure because of the lighter water pushing the heat up. So notwithstanding the fact that it's going up and down, the cylinder and the energy link and everything is up above the stove. And just as with a hot water cylinder, if you heat water with the stove, it wants to rise up. The only reason it will want to come down is because the heat has been stripped off, it's heavier, and it finds a path to come down. The path in this instance is from the cylinder coil up around and up on the return across the attic. It vents again on that little half-inch valve, so that you have no airlock at that point, and drops down into the stove.
And again, the cold feed is on the last.
On the last here. Yeah.
Very good.
Now, keep going. And what are we at here? So we have, again, it's just showing in some situations you come across maybe a basement, or where someone has a boiler lower than maybe in some lower area outside the house, and you might have a higher, the ground floor of the house might be at a higher level of where the boiler is, but it just says that you carry on as before. You have your flow and return rising up from the stove across. We've created the heat lock loop over by the cylinder. We have our heat trap, and we have our half-inch vent releasing the air from the heat trap. We have our bypass valve releasing the air from the return. Again, a very, very safe system.
And again, the cold feed.
Cold feed again.
On the back.
Yeah. Just another. Oh no! Sorry. Here's an interesting one as well. Follow the flow here. You'll see it rises up first of all, and passes through, say, an energy link, and the energy link can strip off the heat. So in that situation, you might go in heat, say, a pressurized cylinder. You still have your heat leak, because when the water is on the way back down, although the heat has been stripped off, any extra heat that's left over passes the return, but now it can travel through heat leak radiators. The main benefit is you're not cooking the heat leak radiators just because you lit the stove. It's only getting the return water going back to the stove. But it's critical to remember the energy link or no secondary system should ever be allowed to draw energy away from the stove until the water reaches 55 degrees. So the stat within the energy link would be set at 55 degrees.
Why do you go with the dump there, Harry? Why do you go top and bottom with the radiators?
It's with a heat leak radiator, it's critical that you get a good gravity circuit, and again, because the heat wants to rise, you
Yes.
let it rise into the radiator. As the radiators cool the water, it falls out the end into the return pipe and back in. So again,
And again, the cold feed is
back
back
into
on
the
the
end.
return.
Yeah. But like all of the things there are established practices for maybe 100 years before anyone ever came up with the more modern pumping method. This was the way it was always done. Extremely safe, extremely effective.
Yeah.
Now, here's an interesting job. Just suppose you have a situation where you want to have, there's a problem with power outage, and you want to have a system. Granted, I know there's a pump on the flow, but the pump would let water pass. But if a house is piped like that, where you rise up to a high point, and I'm talking 1 or 2 meters into a tall attic, and then you vent it up at that point and fall across the attic and drop down to top and bottom connections in radiators. In fact, you don't even necessarily have to have top and bottom connections. Those radiators will work perfectly without the pump operating. So if you lit that fire and it's installed in accordance to the diagram there, the pump is there as an added feature, but the system will actually heat without the pump. Every rad in that house and the hot water will heat without electricity. It's a very interesting system. Now, here so is where you would have a flow leaving the stove, rising up and going to a heat leak radiator up beside the expansion tank. But if you see, there's a non-return valve that stops the heat drift travelling across towards your upstairs radiator circuit, going from right to left. And so your heat leak radiator is fed into the top of the rad and will work perfectly through the rad and fall back down to the stove. When the pump comes on, the water now travels over to your manifold distribution system, for example the energy link, so you can have pressurized water because you're not heating the water directly from the stove. But if you call the pump pointing towards your upstairs radiators on, and it's pushing water up, the water is flowing towards those radiators, but also it's pushing towards the non-return valve, and so it will heat the heat leak radiator as well. There's a little balancing valve that you might see fitted just to the left hand side of the non-return valve, or right hand side. And what that's for is you can regulate how much water is actually going to flow back, so that you won't have the pump pushing all the water over to that open circuit. Remember, with a heat leak radiator, you try not to have it as half-inch pipe. It would be 3/4 or even inch pipe connected to the radiator. That drawing shows valves fitted, but really you're better off by far to have no valves on any heat leak radiator, or if you do have valves, have lock shield valves that are fully open. So with that scenario, you can have a pumped zone upstairs that also heats the heat leak, and you can have a heat leak that won't heat the radiators upstairs until the zones decide to call.
So that could be one radiator or 2 radiators, 3 radiators, whatever.
The more the better, really.
To dissipate the heat from the boiler. So that would calculate how many rads you want, or the size of the radiator, or whatever.
Yeah, typically you go by the manufacturer's instructions, but the rule of thumb is when the stove is fully loaded and
Yes.
is lighting fully,
Yes.
and you turn down the dampers, whatever that heat output is, your heat leak should match that.
Oh, yeah.
Okay. Very good. Okay, lads. I'd like to thank Harry for giving his time on this, and going forward, we would like to do a couple more of these seminars going forward, but it'll be with various companies we have. You know, Harry has promised to come back in another few times to do various add-ons to this. This was just kind of more or less based on gravity systems, so we will be picking other topics as well going forward.
Thanks for your time, lads.
Yeah, thanks very much.
Cheers, lads.